So the first method we took a look at for finding antiderivatives analytically was W substitution. Today we take a look at our second method, which is called integration by parts. So integration by parts is a method for finding antiderivatives of products. So for example, we might want to find the integral of x times the sine of x dx. That's one that substitution will not help us with. Or maybe we want to find the antiderivative of x cubed e to the x. Again, substitution is not going to help us with that kind of integral. And it's also the case that the integral of a product is not equal to the product of the integral, just like the derivative of a product is not the product of the derivatives. So the integration by parts formula is based on the product rule for derivatives, which we'll remind ourselves of in just a moment. And the idea that's underlying the method is we're going to start off with a difficult integral, something like x sine x, and we're going to use the formula to replace that with another integral that will hopefully be simpler for us to evaluate. So first, a review of the product rule. So if we're taking the derivative of f times g, that's going to be the derivative of the first times the second, plus the first times the derivative of the second. And now for the purposes of our discussion today, we're generally dealing with functions u and v. That's kind of the traditional notation. So if we were to look at taking the derivative of u times v, and we suppress the dependence on x, in other words, we just don't write the dependence on x, then the derivative of u times v would be u prime v plus uv prime. So we'll take a couple of moments to derive the parts formula. It's not a long proof, but it is good, I think, to see where the formula comes from. So we start with our previous application of the product rule for derivatives. So here's our derivative of u times v again. So u prime v plus uv prime. So starting with that, we're going to integrate both sides. So we end up with integrals on the left and integrals on the right. And we know that those two sides are still equal. And now on the left-hand side, the integral of uv all prime is just the integral of a derivative. So when you integrate a derivative, you get the original function back again. So taking the integral of uv prime just gives us the original function. Well, that's more or less enough to get us to the parts formula. All we have to do now is just reorganize this a little bit. We move the integral of u prime v over to the left by subtracting it from both sides. And so what we get is down here, and then just using the sort of standard practice, I've flipped the equation so that the right-hand side in the original is now the left-hand side. So we have the parts formula, the integral of uv prime dx equals u times v minus the integral of u prime v dx. Now it doesn't appear here like we've done any good, but the idea from before, the big idea underlying the method, is that in our examples, we'll set this up so the integral on the right is an easier integral to do. So that's the goal. So now we talk about how to apply the parts formula. So it's going to be up to us to figure out what the u is going to be in the integral and what the v prime is going to be. Now we have sort of general guidelines. Like a lot of things, these don't apply in every situation, but generally speaking, we're going to select u to be the part of the integrand whose derivative gets simpler, which leaves the rest of the integrand to be v prime. So that has to be something that we know how to integrate. So for example, if we take a look at the ones I wrote before, if we were doing the integral of x sine x, well, if I tried to let sine x be u, then the derivative would be cosine x. That's not really any simpler, it's about the same. But if I let u be equal to x, then the derivative of x would just be 1, which is simpler. That would leave v prime to be the sine x, and that is something we know how to integrate. The integral of sine x is minus the cosine. So that's how we would make the selection in this first example. In our second example, we had something like x cubed times e to the x dx. If I let u be e to the x, its derivative is itself. It's not really simpler. It's no worse, but it's not simpler. X cubed, however, if I take the derivative of x cubed, I would get 3x squared. And x squared is a little bit simpler than x cubed. So that would be a good choice for u in that case. And that leaves v prime to be my e to the x, and that is something we know how to integrate. The integral of e to the x is just itself. So in these two beginning examples, we see how we might select the u and the v prime to then go ahead and apply the formula. So our first example will be a straightforward application of the formula. So our first example is to find an antiderivative for x times e to the x. We want to use integration by parts, which means we need to decide what's going to be u and what's going to be v prime. Remember that our general rule is that u needs to be a part of the integral whose derivative is simpler. And then v prime is whatever's left, and it has to be something we can integrate. So here, it looks like if we let u be equal to x, then that should work because u prime is the derivative of x, or just 1, which is simpler. Now, what's left is v prime has to be equal to e to the x. Now that's okay too, because the integral of v prime is the integral of e to the x, and that's just itself. So when we apply the integration by parts formula, the original integral will be equal to u times v minus the integral of v u prime. With our selections u equal to x and v prime equal to e to the x, my u times v becomes x e to the x, and my v u prime is just e to the x times 1 dx. Now what we've done is transform what was a difficult integral into one that we can do. We get x e to the x minus the integral of e to the x, and the integral of e to the x is just itself. And then the last thing for us to remember is just to add the constant of integration. So we get a plus c, and that should be our final answer. Our second example will be one where we have to apply the integration by parts formula more than once. Our next example is an application of integration by parts, but one where we actually have to apply the parts formula more than once. So, as usual, our first job is to figure out what should be the u and what should be the v prime. Here, I'm going to let u be x squared, because x squared is something whose derivative, 2x, is a little bit simpler. So u will be my x squared, which makes u prime equal to 2x. So if u is equal to x squared, my choice for v prime will be sine x. So v prime is sine x, which means I need to know the integral of sine x, or antiderivative for sine x, and that will be minus cosine x. Applying the parts formula, my original integral will equal u times v minus the integral of v u prime. And now we fill in the u's and the v's according to our choices. My u was x squared, and my v is minus cosine x. And then I subtract the integral of u prime times v, which is minus cosine x again. And then if I clean up the minus signs, I get minus x squared cosine x plus the integral of 2x cosine x dx. So here's why this problem is a little harder than the previous example. The integral that I have arranged by using the parts formula is simpler than the original, but still not one that we immediately recognize. So we have to use parts again. We want to find a u that gets simpler when we take the derivative. So I'm going to let u equal 2x. So then my u prime is 2. The v prime is what's left, and that's my cosine x. And so I need the integral of cosine, or antiderivative for cosine, which is sine x, because the derivative of sine is cosine. Now I need to apply the parts formula to the integral. I still have my minus x squared cosine x from before, and now in place of the integral, I need u times v, so that's 2x sine x minus the integral of v u prime, or u prime v, that's 2 sine x dx. So I now have an integral, let me clean this up a little bit, that I think we can do. So from before, minus x squared cosine x plus 2x sine x minus the integral of 2 sine x dx. So the last thing to do is evaluate the final integral. And because we've used parts twice, we took the original integral that involved an x squared and replaced it by one that just involves sine. So the integral of sine would be a minus cosine. So I would get a minus -2 cosine x. Don't forget the constant of integration plus c. And I guess I could rewrite this one more time to get the minus signs to cancel. And so we have our final answer. The original integral, x squared sine x, is minus x squared cosine x plus 2x sine x plus 2 cosine x plus a constant. A third example is one that's kind of a tricky application of the parts formula, where we have to recognize that one of the parts of the integral is an understood one. Our next example is to find the antiderivative for the natural log function. This is an interesting example because it's kind of a clever application of the integration by parts formula, and it's for a function we don't already know how to integrate. So for most of our common functions like sine x, cosine x, e to the x, we already know antiderivatives for those, but this one has kind of been left hanging, and integration by parts gives us kind of a neat way of actually figuring out this integral. What makes it kind of a tricky application of integration by parts is it looks like there's only one part, that's the natural log of x. So in order to apply the formula, we first have to rewrite the integral to make our second part appear. And the idea is we're just going to write in the understood 1. So instead of log x, now we have 1 times log x. Now we have two parts to the integral, which means we have a decision to make about what's going to be u and what's going to be v prime. U has to be something that we can take the derivative of, and hopefully it'll get simpler. 1 would work for that, because the derivative of the constant 1 would be 0. But then that would leave v prime to be log x, and we would need to know the integral for that, and that's what we're trying to find. So u can't be 1, which means there's only one thing it can be, and that's going to be natural log x. So we'll let u be natural log x, which means u prime is the derivative of log x, or 1 over x. So this leaves v prime equal to 1. And so v is the integral of the constant 1, which would just be x. Now applying our parts formula, we get u times v. So I'm going to write that as, well, it's natural log x times x. I'll write that as x times natural log x. And then minus the integral of v u prime. So that's going to be x times 1 over x dx. All right, so I can simplify inside the integral. And instead of x times 1 over x, I just get 1 because the x's cancel. So now the integral we started with, natural log x, has reduced using the parts formula to just finding the integral of 1. That integral is just x, and we remember our constant of integration. So for our final answer, the integral of natural log x is x log x minus x plus a constant. Our next example represents what are often thought of as the hardest kind of integration by parts problems, where not only do we have to do the parts formula more than once, and it can be a little messy when we do, but then we have some algebra to do at the end to actually solve for the integral that we're trying to find. Our next example is kind of a challenging example. This is a kind of integral that's going to require integration by parts more than once, which we've done before, but at the end it's also going to require some algebra that might be a little bit unfamiliar to us. So we have two parts to the integral, an exponential part, e to the 2x, and a trig part, which is the cosine of 3x, and we have to decide what are we going to make u and what are we going to make v prime. There's not really a clear-cut choice here as to which should be which, but the good news is that it won't actually matter. So we can select u to be either part, and we'll end up being just fine. I'm going to let u be the exponential part, e to the 2x. And now when I go to find u prime, I do have to be a little bit careful to remember the chain rule here. So the derivative of e to the 2x is e to the 2x, and then the derivative of 2x gives me the factor of 2. So with that as my choice for u, my choice for v prime will be cosine of 3x and so I need the antiderivative for cosine of 3x. That's going to be sine of 3x, because the antiderivative of cosine is sine. But then again, because of the chain rule, I have to divide the sine of 3x by 3. The reason is if I took the derivative of sine of 3x, I would get cosine of 3x times by the chain rule of 3. And so that 3 in the denominator will compensate for it and give me the proper v prime. So I need to apply the integration by parts formula. So that's going to be u times v, e to the 2x times sine of 3x over 3 minus the integral of v u prime. So my u prime I'll keep here as 2e to the 2x, and my v is sine 3x all over 3 dx. So I have a couple of options here. One thing I can do is I can clean up the constants a little bit and get 1/3 e to the 2x times the sine of 3x minus the integral where I've pulled the 2/3 out front. So that's going to leave me with an e to the 2x sine of 3x dx inside the integral. Okay, so I've completed my first application of the parts formula, and what I'm faced with now is an integral that looks very similar to the original, except instead of a cosine, I have a sine inside the integral. So what we're going to do is integration by parts a second time. I still have the same choice facing me as before, what's going to be u and what's going to be v prime. what's important here is to be consistent in the way we've selected u and v prime. So since I let u be the exponential part in the first application of parts, I'll let it be the u in the second application of parts as well. So my u will still be the exponential, which means the u prime is again 2e to the 2x. And that leaves v prime to be the sine of 3x. I have to integrate v prime and keep in mind the chain rule. So that's going to be a minus cosine 3x divided by 3. All right, so I'm going to start a new line where I will apply the parts formula for a second time. So I'm going to have from before my 1/3 e to the 2x sine of 3x minus 2/3. And now instead of the integral, I have my second application of the parts formula. So my new u times v will give me e to the 2x times minus cosine 3x all over 3. And then I subtract the vu prime integral. Write the u prime first here, so I get 2e to the 2x, and then the v by minus cosine 3x over 3 dx. And that completes the second application of the parts formula. All right, so now I have some cleaning up to do to get this to be a little bit easier to deal with. So I want to write 1/3 e to the 2x sine 3x. I'm going to distribute my minus 2/3, so that's going to give me positive 2/9 e to the 2x cosine 3x. And then if I distribute that minus 2/3 to the integral, notice that I have another minus 2/3 that's sitting inside the integral, and then I have a third minus sign in front of the integral. So all told, if I collect my constants out in front of the integral, I should get minus 4/9 times the integral of e to the 2x cosine 3x dx. Now here's where it looks like we have not really done much good. We've done integration by parts twice, and where we've ended up is here with the same integral we started with, e to the 2x cosine 3x. So here's where we actually have to do a little bit of algebra. I'm going to rewrite the original integral on the left. So all the work we've done equals the integral e to the 2x cosine 3x dx. So what we're going to do is we're going to take this integral and move it to the left-hand side. So when I say move it, what I mean is we're going to add 4/9 of the unknown integral to both sides of our equation. So what that's going to do is it's going to make the left-hand side look like the following. The integral e to the 2x cosine 3x dx plus 4/9 of the integral e to the 2x cosine 3x dx. And I know that that equals 1/3 e to the 2x sine of 3x plus 2/9 e to the 2x cosine 3x. On the left, I can combine the two integrals. So I have 1 times the integral plus 4/9 times the integral, and that gives me 13/9 times the integral that I'm trying to figure out, e to the 2x cosine 3x dx. And this is equal to what we had before, 1/3 e to the 2x sine 3x plus 2/9 e to the 2x cosine 3x. Now the last thing to do is solve for the unknown integral. If I know what 13/9 of the integral is, then I can multiply both sides by 9/13, and that will give me the result that I need. So multiply the left by 9/13 and multiply on the right by 9/13, and we'll be done. So on the left-hand side, I get the original integral by itself now. And on the right-hand side, I get 9/39 e to the 2x sine 3x plus 9/13 times 2/9. The 9's cancel and will give me 2/13 times e to the 2x cosine 3x. And as usual, we have to remember, since we have an indefinite integral, we have the constant of integration plus c. And finally, we have our final result. So to summarize what we've done with integration by parts, the idea is that the formula can exchange a difficult integral for an easier one. The general guidelines for selecting u and v prime is that u should be taken so that u prime is simpler, and v prime has to be something we can integrate. Sometimes the v prime is kind of hidden. It's an understood one in the problem, and sometimes we have to use parts more than once. Sometimes we use parts more than once and end up back at the original integral, and then we have to solve for it using some algebra. Well, that's going to do it for our integration by parts section. Coming up next, we'll have another technique for finding antiderivatives. That's called integration by partial fractions.